So its greater Vita is there because not only that, well, Vita can answer any questions that I don't know the answers to, so that's kind of good. Nevertheless, let us start. So what the problem is, we begin a positive definite quadratic form, and this positive definite quadratic form over rational integers in this case. So aij are rational integers, and this form is in the R variables, or sometimes you're going to say this forms of rank R. There's some vector in z to the r such that this equation qx equals to n satisfied. So we either say that q represents n or n is represented by q. And so a question for us is which integers are represented by a given form. And we all met some examples of this problem. For example, we know that x squared plus y squared and odd prime, if and only if this prime is congruent to 1 mod 4. Probably a slightly less known example is this Ramanujan-Tannery form, which says that x squared plus y squared plus 10z squared represent all odd integers, but they need to be larger than 2719. And this result was proven only conditional on GRH in 1997 by On and Sundararajan. And perhaps a bit, again, more known result that any natural number can be represented as a sum of four squares. And so this kind of forms which represent all natural numbers, and given that our quadratic form is positive definite, so this form represents all eligible numbers, or at least all the numbers we expected to represent. This kind of forms we call universal. So we say the quadratic form is universal if it represents all positive integers. And this is the question for us, really. So this talk going to be mainly focused on these universal forms. And the question for us, which forms are universal? As I showed before, the four squares is universal. And we know from local theories that no form in 3 variables can be ever universal over rational integers. Therefore, if you want to classify all the forms of rank 4 or in 4 variables, this was done by Ramanujan and Dixon, and they classified all the diagonal quadratic forms in 4 variables. So this was early result in this area. But there was quite a big update in past 30 years. So the first result came in so-called number theorems. So Conway and his bachelor student Schneeberger, they proved this theorem 15. So theorem 15 says if you have a classical positive definite form, and by classical, it means that if you consider the corresponding gram matrix, the gram matrix going to have integer coefficients. So the matrix, you're going to get a rational integer symmetric matrix. So if you have this classical positive definite quadratic form, then this form is universal over rational integers if it represents all integers between 1 and 15. Right? So you have the finite numbers you need to check, and if your form represents these numbers, then your form is universal. And later, this got improved slightly. So it was not slightly, but quite a lot. So it was improved by Bhargava and Hanke in 2011. And they show that given any positive definite quadratic form, so now here the matrix doesn't have to be integer, the gram matrix. So given any positive definite quadratic form over integers, it is universal if and only if it represents all integers between 1 and 290. Okay, so now we can see that there's a big difference between these two problems. Even the proofs are, there's a stark difference between proofs. So the proof for theorem 15 is quite elementary in some sense, while proof for 290 theorems involves much more technical tools. So it's a paper which haven't been published as yet, although it is available since 2011. And so one would want to know whether one can improve this list of 290 integers. And the answer is no. So for any of the integers in this list, we can forget one of the integer and there exists a form which represents all these integers, but doesn't represent this missing integer. So in some sense, this list is optimal. And finally, another example of this kind of number theorems is 451 theorem. So it's a theorem by Rouse, and it says that if positive definite integer quadratic form represents all integers between 1 and 451, then it represents all odd integers. So so this result is actually you need to assume GRH for this result, or you can assume slightly weaker condition to have this result. But this is kind of a flavor of number theorems that we have. And essentially, this number theorems, they give us good picture of what we know over rational integers. And what I want to present to you, how these ideas and how these problems can be tackled over number fields. So let us maybe go here. So by number field today, I will always mean totally real number field. So we have K going to be totally real number field of degree D. By that, I mean that every embedding of our number field is actually embedding into R. By ZK, I'm going to denote it brain of integers. And so the two prominent examples of these number fields are real quadratics. So the Q adjoins square root of D, some square root of positive integer D, or the totally real maximal subfield of cyclotomics. This is also a really good example for us to study generally. And we're going to say that algebraic integer alpha or algebraic number alpha is totally positive, and we denote it by this squiggly line. If under every embedding this of our number field, this integer is positive. Right? So if you think about Minkowski space, this integer gonna live in the totally positive quadrant, so where all the coordinates are positive. And now we want to extend the definition of universality for this number fields. So we say that our quadratic form is universal over ZK. So first of all, we want it to be totally positive definite, by which we mean that when we take our matrix Q or our quadratic form Q under each embedding, it's a positive definite quadratic form. And this makes sense because each of our embedding is into real numbers. So now we have that our quadratic form has to be totally positive definite, and throughout the talk, all the forms going to be totally positive definite. And finally, we want for our form to be universal. We want it to represent all the eligible integers, so all the totally positive integers. And let me now just give you some sample of results we know over number fields. So first of all, we know that 3 squares represent all the totally positive integers over Q adjoins square root of 5. This is the result of mass. And as you see, there's already stark difference between rational integers and number fields, because here we already have a form in 3 variables, which is universal. And one can assume that perhaps for any number field, you just it's sufficient just to add more squares and then it will be universal. However, this is not so. So result by Siegel says that if you have any finite sum of squares and it is universal over a ring of integers over a totally real number field, then this number field has to be either Q adjoins square root of 5 as here, or it has to be rational integers. Right, so the only 2 cases where rational integers can be universal, sum of squares can be universal are these 2 fields. Furthermore, this case of having ternary universal form, we know this is less common. So for example, we know no ternary universal quadratic form can exist over a number field of odd degree. So for this case, you always need to have even degree, which is the case here. And in some sense, this also explains why we don't have a universal form over rational integers in 3 variables, because it's trivially or extension of odd degree. And speaking of universal forms in 3 variables, there's extremely important conjecture in this area, which is called Kitaoka conjecture, which says that there are only finitely many totally real number fields which have a ternary universal quadratic form. So this would be one of them, and so we don't know the complete answer for this conjecture as yet. So Perhaps I can now explain what is known for the smallest number field they can think of. So real quadratic number fields are really good. And we kind of know a bit more here than in other degrees. So throughout, let me denote by L the real quadratic number field. And so what we know here? First of all, we know that if we have a real quadratic number field over which there are only finitely many real quadratic number fields over which there exists universal quadratic form in 7 or less variables or fewer variables. This is a recent result by Kim, and Park. And so one would want to know what happened when you consider 8 variables. And here we know that actually we have infinitely many number fields with 8 variables universal quadratic form, right? So between 3 and 7, we have finitely many number fields. And as soon as we reach point 8, we have infinitely many number fields. Now, we also know that result by Blomer and Kalla that the rank of universal form over a real quadratic number field is unbounded. So for any natural number m, there exists some number field where m variables will not be sufficient to create a universal quadratic form. So you need to have more variables. And in the recent result in joint work with Kalla, Zmija, and me, we show that the universal forms in n variables, there are no universal quadratic form in n variable for almost all real quadratic number fields. So the density of number fields over which you have universal form in 8 variables have natural density 0. And let me maybe give you some sort of a flavor of what goes into proof of this theorem. So the idea here, for simplicity, I will assume that our quadratic number field is L Q adjoint square root of D, and I will pick a D to be congruent to 2 or 3 mod 4, but result does hold for congruent to 1 mod 4 also. And what we do here, we consider the continued fraction expansion of our square root of D here. So we have here U1, U2, UR, and so this periodic part. So this is continued fraction. And the result of Kalla and Tinkova shows that if our ring of integers z to the L has a universal quadratic form, then this universal form needs more than u2 to the I plus 1 over 2 variables. So you could consider the maximum of the odd periods here, odd coefficients in this continued form, and this is going to give you a lower bound for the rank of universal quadratic form. And so what we do in this paper, we show that if you look at all the d's between 1 and x, for which the odd parts of a continued fraction expansion is bounded by m, then the natural density of the set is 0 as x goes to infinity. Now I'm slightly cheating here because obviously we need to normalize that we get rid of this u to the 0. We need to get rid of it so it's going to be 0, but nevertheless that's kind of the gist of the paper, which hopefully going to be finished by the end of this year, and you will be able to have a look at it. And so this gives us really nice idea what we have over real quadratic fields. However, over a larger number field, much less is known. But we are able to give some not bad lower and upper bounds for our quadratic forms. So in particular, for upper bounds, we assume the K just to be any totally real number field of degree D. And I'll denote by delta K is discriminant. And we'll need the following lemma. So the lemma says that if we have totally positive integer alpha, whose norm is bigger than discriminant, then we can decompose this alpha as some totally positive element gamma plus a square. Right, so essentially it says that if element has too big of a norm, you can decompose it in 2 parts, where one is a square and the second element is totally positive element. And so we use this, so I can actually show you the proof of this lemma, so it's quite nice, using some geometry of number. So we consider the box defined by the embedding, square root the embeddings of our element alpha. So we assume here the alpha is of this norm. Now, based on this definition, we know the volume of this box is greater than 2 to the d square root of discriminant. Now, using Minkowski theorem, we know we have a non-zero integer point in our zk, which lives in this box. And so we now have that under each embedding, this beta element here is bounded by square root of sigma alpha. Now we square in and rearrange in, and we get this element alpha gamma, which is going to be totally positive by this inequality. So we use this lemma to prove the following theorem. So we show that universal quadratic form over any totally real number field of degree d has fewer than discriminant to the k log of discriminant to d minus 1 variables. And the idea of the proof is the following. So from the lemma, we know that any totally positive integer can be written as some gamma plus a sum of squares. So we just do it recursively. We take any element alpha. If it's norm too big, we decompose it with a lemma. If then we get some gamma there in decomposition. If its norm is too bigger than discriminant, then we decompose it again. Otherwise, we stop and we get this element of a norm bounded by discriminant. Now, to deal with this sum of squares, we need to use so-called Pythagoras numbers. So every finite sum of squares of z to the k can be represented by finite sums of squares. And this number is invariant for the number field. So the p to the k sometimes is called the Pythagoras number. And we know that this number can be bounded by something which depends only on the degree of the extension. So the upper bound on this Pythagoras number is independent of the number field. Right, so essentially we can already bound this sum of squares which we have for representing any element alpha. So it just leaves us to deal with element gamma now. And so what we need to do really here is to find find all the representatives of elements whose norm is bounded by discriminant of our number field. And to do that, we just count the number of ideals whose norm is bounded by the discriminant over a number field. And for that, we get exactly this bound, which is discriminant over k log to the discriminant to d minus 1. And so we get it. So this is only conditional on the degree. Again, so it's independent of the number field. This is how we get a lower bound. Upper bound. So for the lower bound, we have this a bit more technical theorem. So it says that fixing any natural numbers d and r, there are only finitely many total real number fields who are primitive, monogenic of degree d that have units of every signature and universal quadratic form of rank r defined over them. Let me maybe just decompose or explain some of these terms. I know there were talks about monogenic number field before, so maybe it's more familiar. But by monogenic, I just mean that the ring of integers have a power basis. So our ring of integers z to the k can be written as z adjoins some algebraic integer in our number field k. By primitive I mean that there's no intermediate number field between k and q. So and by units of every signature, I mean that for any algebraic integer in our number field or algebraic number, there exists a unit such that it's by multiplying by this unit, we can always make this element alpha totally positive. Okay, so this is 3 conditions we need to satisfy. And let me sketch how we use these conditions to prove the theorem. So when we have a monogenic number field, it means that the dual of our ring or a codifferent is principal ideal, right? So by dual, I mean all the algebraic numbers such that its trace when multiplied by algebraic integer is integer. Now, given that we have units of every signature, we can assume this delta here is totally positive by multiplying by correct unit. Now, if you have universal form Q, then Q represents all the totally positive integers in Z to the K. But when we multiply our Q by delta, which is totally positive, here it's represent all totally positive integers in our dual now. So essentially what it means that our delta Q represents all the totally positive integers in the codifferent. Now, because of that, we can take a trace of our delta Q, and this is going to be integer matrix now. So if Q has a rank R, then trace of delta Q is going to be now a positive definite quadratic form of rational integers, and its rank going to be R to the D. Right, so D is fixed because D is just a degree of our extension, and R is the rank of our quadratic form. So R to the D is fixed. So now what we want to have a look at is that the smallest element with respect to trace in this codifferent. So we want to check the smallest elements here. So essentially we have that each totally positive number gamma in a codifferent of trace 1 will correspond to the minimal vector of our quadratic form trace of delta Q. So it's going to be minimal vector of this integer quadratic form. Now, using primitivity, we can show that number of these elements of trace 1 grows with the discriminant of the number field. But we also know that the maximal number of minimal vectors in a quadratic form is bounded by the degree, or by the rank, sorry. So we have that the rank is bounded because it's R to the D, but we know that given that the discriminant grows in a given degree, we know that this cannot be satisfied, so the rank has to grow also. So this result gives us a lower bound for the rank of universal quadratic form. So before I go to a bit more of the auxiliary problems, perhaps some of you may have any questions. No?
Yeah, so in your theorem, in the last theorem, if you drop those conditions, do you still expect finiteness? Like, let's fix a rank R for your universal form. And
so some conditions I think can be loosened, but not all of them.
No,
because
not for a proof. Would you expect finitely many number fields, or would you expect there to be infinitely many number fields for which this would be the universal?
Perhaps no, perhaps no. So I think that there's so as you saw in real quadratic number field, yes. At some point we have finitely many number fields over which you have a quadratic form with bounded number of variables. However, there's some critical point or phase change where you start getting infinitely many. And so it means that just assuming this result, it means that for this infinitely many cases, one of these conditions cannot hold, because this theorem states for any number field. There's no restriction on degree. So I'm not sure if I answered your question, but I think I answered my question. So
I have a question about your number theorem that you had earlier, this 15 theorem and 290.
Oh yeah.
Etc. So if are there any results which will not give you universal quadratic forms, but something which eventually represents every positive integer?
So there are results like that. Obviously, it's so results like that always depend on a number of variables. So
but of this nature, of this number theorem kind of nature,
of number theorem, I'm actually highly non-sure. So the result, which is by Ono and Sundararajan, this is kind of result in this direction, which says that you represent all sufficiently large integers.
Right.
But whether it would hold in general, I wouldn't know really.
Thank you.
But there are results for sum of squares, where we know over totally real number fields, over totally real number fields, quadratic form in sum of 3 squares represent all sufficiently large integers, which are locally represented, And if you have more variables, similar results do hold also. But there's no numbers associated, so there's no number style theorem for that.
Thanks.
It's more like local global condition. Okay, so I will continue. So for the last 5 slides, I will maybe switch the topic slightly, but not too much. So it's a further results. So one of this deviation is so-called Z-forms. The question is, can the quadratic form with rational integer coefficients, also called Z-form for us, so positive definite quadratic form with integer coefficients, be ever universal of totally real number field, right? And so this is exactly the kind of question that Siegel asks. So the sum of squares is exactly this form, so this form with integer coefficients. And Siegel and Mars showed, as I showed previously, that this form can be universal only over these 2 number fields, whether it's rational integers or the Q adjoint square root of 5. So me and Vita found another example. We found the example of degree 4. So this is quadratic form in 4 variables over Q adjoint this totally real part of roots of unity. And so this is a quadratic, so note that this number field is of degree 3. And so we know that there cannot exist a universal quadratic form in 3 variables because it's an odd extension. So in this number field, this is actually the smallest quadratic form with respect to a number of variables you can find here. And more generally, we show this result for the low degrees. We show that given a totally real number field of degrees 1, 2, 3, 4, 5, and 7, so 6 here not emitted by a mistake, such number field for which the codifferent in principle, and it has universal quadratic form defined over them, then this number field has to be one of these number fields mentioned above. So it needs to be either our rational integers, Q adjoint square root of 5, or this maximal real subfield of 7th root of unity. And let me just give you glimpses of ideas what we used here. So again, as in previous theorem, we use this condition that if you have a codifferent which is principal, then we can have can represent it as such, some delta times our ring of integers. And due to the condition on the Z form, we get again that we have units of every signature again. So we have it for free here. Now, instead of thinking here in terms of trace of delta Q as before, we can view it here as a tensor product of 2 quadratic forms. And this is this works because we assume the Q is Z form. Now, we use this to show that every totally positive integer of trace 1 in our codifferent actually have to be a unit. So we show this. So all those elements which would be minimal vectors of this quadratic form, in this case, they need to be also units in our corresponding element, needs to be unit in our number field. And now we use Dedekind zeta function to bound the discriminant of our possible number fields where this is possible. Specifically for degrees 2, 3, 4, 5, and 7, when we evaluate Dedekind zeta function at 2, we have the following description. So we have some terms here which depend only on the degree extension. Then we have our discriminant. And then we have sums over the divisor function over all the elements of trace 1. And so here, this is the reason why we omit here 6, a degree 6 extension, because in degree 6 extension, we also would need to consider elements of trace 2. And the same condition would hold for any larger number fields also, any larger degrees. So this is this identity is due to Siegel. And what we need to note here is that given that each of this gamma of trace 1 correspond to the unit, each contribution here from this gamma is just going to be 1. So we have kind of good control for this contribution. And with this, we bound all the possible discriminants where we need to check it. And then we check this finitely many number fields, and the result kind of follows. So the last part is slightly computational. After we find the bounds on discriminant, we need to just look at every discriminant and check, and that's what we did. And recently, we extended this result in a slightly different direction. So we show that for each degree D, the at most finitely many totally real number fields of degree D with universal Z form. And the idea here for a proof is different completely in some sense. So we study here representing all the totally positive integers which are divisible by some rational integer by sum of squares. Right, so you take any sum of squares, and you want the sum of squares to represent all integers which are, for example, divisible by 2. So for the example, so what we showed actually is that for if we fix our M and degree, there are only finitely many such number fields of degree D where this is possible. And if you think about for the smallest case was M equal 1, this is exactly what Siegel showed, and he actually showed there's only a finite number of such fields in total, so there's only 2. And as another consequence of this result, we have a weaker version of Kitaoka conjecture. So we showed that there are only finitely many number fields of degree D with universal ternary quadratic form. So this completes my talk. Thanks a lot. I think I rushed a bit, but well, I think it's. Yeah, I couldn't hear the applause, so I muted applause.
Is there any question from the audience?
Yes, my question is that what is the significance of the codifferent is principal? What is the if it is not principal, then what will happen?
Well, if it's not principal, then we cannot multiply our quadratic form just by single variable to get this nice idea. So here we just always use this idea that if it's principal, we have a quadratic form which is universal, and then it represents all the elements in the codifferent. When it's not principal, we can't find just a single element to multiply it by to represent everything inside. And perhaps this can be extended in somehow, but it's going to be a bit more fiddly. And so we haven't thought too much about it, how to deal with this non-principality condition as yet.
Any other question?
I can maybe make a comment related to Anup's question. So actually Pavlo is working on so concerning these assumptions on monogenic units of all signatures and primitive. So as far as I know, Pavlo is working on removing some of these assumptions. So it seems that to some extent, he and my student might be able to remove the primitive assumption. And actually the units are crucial to some extent, but probably you don't need all units, but you just need some specific signature of units.
Yeah, that is true.
Okay. Any other question? Otherwise, let's give thanks to our speaker again.
If there is any online.
Any audience online?
So chart is clear, unless go in.
Thank you. Okay, thank you very much. Professor Pavlo.
Yes.
Thank you.
Thanks a lot, Pablo. It's very nice.
Okay, thanks.